Good afternoon. So I'm going to be presenting on my Keystone, which is also my capstone for my College of Engineering end of school career. And we worked on designing and prototyping an improved electrosurgical device. So just to give a little bit of background on what electrosurgery is, it is the application of high frequency alternating current to cut, coagulate, desiccate, or fulgurate biological tissue. And that basically means that a rod is electrified, a metal rod is electrified to get really, really hot and heat up bodily tissue so that it can actually melt it at a really low level, which leads to these different applications. It can be used for major tissue dissections or to just surface level cuts with warts and other skin defects. Um, and this is something that's extremely important because in solid organ dissection, post-op complications are really common. And hemorrhaging can happen in 20 to 40% of surgeries. Plus, hemorrhaging is the most common cause of mortality, of higher mortality and morbidity rates in surgery. So trying to make this better is a very important thing to focus on. So a little background on the project. This was commissioned by Dr. Omar Barakat of Baylor. The project actually started within the College of Engineering last year. The concept is to simplify these multi-tool operations during surgery so that it's easier and more intuitive for surgeons and that they can respond more quickly to sudden changes. Our team consisted of myself and three other undergraduates, Zach Weiss, Celeste Figueroa, Elizabeth Barber, and all of these engineering professors and mentors. So to define the project, our goal is to create an improved electrosurgical device that allows for minimal to no blood loss. The differences between our device and existing electrosurgery devices are to implement an oscillating tip so that we can separate the blood, biological tissue from blood vessels. Tissue has a lot of pockets in it that make it so that it's hard to kind of separate things and get get inside the body to certain points that surgeons might need to cauterize or stop bleeding in. And implementing this oscillating tip makes it so that that tissue is more easily accessible. We want to implement as well a saline drip to irrigate the tissue and on-device controls so surgeons can control how fast the tip is oscillating and the level of power they're applying to the bodily tissue. So our design process began by building upon the work of the team last year that started with this project. The main focus for us while we have this project is to implement electrical connectivity. So having an oscillating tip rather than a static one, which does not move, means that maintaining electrical connection was going to be a challenge, and we wanted to make sure that we could maintain the electricity in the rod at all times. We also want to be able to waterproof the case when you have parts that are moving both inside and outside of a case. The waterproofing is really important, especially when it's going to be in the body, because you don't want any bodily fluids to get in, and you also want to make it very easy to clean. Then we want to integrate onboard controls, like I was talking about, to control speed and power and integrate the saline drip. So our plan for electrical connectivity, or the last year's team's plan, was first to electrify the probe via a slip ring. So what that would do is have the electrical rod would be touching the inside of the ring at all times while it was oscillating to electrify it. But this was not feasible because of the high RPM that we were going for and the inconsistency of contact within the slip ring, because the oscillation is not 100% predictable. Instead, we decided to clamp a wire near the pivot point, which you can kind of see in our picture here. That way, since the rod is not moving at the pivot point, it made a good spot where the wire wouldn't be moving as well. There shouldn't be too much wear and tear, and there shouldn't be loss of connection. When we did stress testing over the course of 24 full hours of running it, we got good results and maintained electrical connectivity. We also updated designs for the motor key, which is something that we attach to our motor to offset the rotation of the rod so that it oscillates as we would like it to. And we also changed the case. So we had sizing differences with our motor, and we had to redesign the case that last year's team had, as well as the motor key, to fit onto this new motor. We switched from a testing motor to a medical grade small motor, and that actually was really good in helping with ergonomics as well as the oscillation of the tip. So it made the case a lot smaller, so it was more comfortable to hold in your hand, which is really important during surgery. So this is a video of the oscillation of the tip. The motor key is on the left here and it's spinning around, and the pivot point is this black rubber piece. It's called a grommet that goes right here. So there's no movement, and this is where the electrical wire is going to provide the power to the rod. So after figuring out electrical connectivity, we had to move on to waterproofing. For sanitary use in a medical environment, we had a twofold approach. So the first one was, because a majority of our manufacturing was done via 3D printing, we sealed the exterior with an epoxy resin so that any small gaps in the printed material were covered. At the pivot point, we press fit this rubber grommet, which you see on the right here, because that made it so it was completely waterproof if the case was submerged in water. We tested this by submerging the case with all the parts inside in a dyed liquid, and we put a paper towel inside the case so that once we took it out of the liquid, we could see if the paper towel had any coloring in it. And after up to an hour of being submerged, it was resilient and it did not absorb any of the water. So what we're working on right now is integrating PWM controls to help to enable surgeons to control the motor speed and the electrical connection, or the electrical power that is inputted into the rod. We have a saline bag and drip line as well, acquired from Tufts Medical Center, so we were able to start to work on integrating that. And then we want to continue to revise the case to fit an external drip line and the PWM controller buttons, so that surgeons actually have all of these accessible on the case. So in the future, the main thing that needs to be done is actually apply higher voltages with our design to tissue. So because of the voltages that are usually involved in these surgeries, which are up to 100 volts, it couldn't be safely done during the Learn from Anywhere process. It requires in-person monitoring that we couldn't get, but the initial testing phase will just be grabbing tissue from a meat market like a liver or a kidney, and applying the electrical current at this higher level, making sure that the tissue is reacting as we expect it to. And then secondary testing phase will be animal trials, and then it will hopefully be able to move into hospital rooms. And then DFM, DFA, regulatory compliance, these are just things that relate to the actual design of the device to make sure it's following engineering guidelines. And I want to acknowledge all these people. Already talked about them in the beginning, but as well as the people who worked on this project with us. I want to thank the KHC administration and community for all their support throughout this process. And thank you all very much.